Right.
All right, hi everyone, and welcome to today's seminar. Today I'm happy to introduce Cole Dorman. Cole got his undergraduate at the University of Iowa working on magnetometers with Dr. David Miles. He is now in his second year of a PhD program at the University of Michigan and has recently received a NASA Finance grant, which he is utilizing to complete his PhD studies and complete his studies on in situ magnetometers. He's currently working in the Climate Space Department with Dr. Mark Moldwin and is largely focusing on the engineering side of magnetometers, which he will discuss with us today in the development of self-calibrating magnetoinductive sensors for spaceflight constellations. Cole, if you'd like to take it away.
Thank you very much for the introduction. Good morning, good afternoon, everyone. Like Kyle said, we'll be talking about the development of these sensors and turning commercial sensors into a self-calibrating device for spacecraft missions, referred to as constellations, which have tens to dozens of spacecraft. All right, so seeing as we're the magnetospheric online seminar series, I don't think we need too much of a background in the importance of magnetic fields, but as I'm sure we all know, they're a fundamental parameter to space plasmas. And because of this, magnetometers are a quite important instrument for spacecraft. But despite this, common spaceflight magnetometers can create a lot of different constraints for spacecraft, either due to the mass of the magnetometer, its volume, the power required for the magnetometer, or how much the magnetometer costs. And so because of this, a lot of these common calibration techniques, while might be effective, have their own pros and cons and trade-offs. So commonly, magnetometers on spacecraft can be calibrated through the use of a vector magnetometer, like a flux gate magnetometer, its absolute value being compared to a scalar magnetometer, like an atomic, a sensor that measures the common, well-known energy transitions. And so while this is very precise and accurate and incredibly stable, it can cost a lot of money. Another method for calibrating different magnetometers is to compare the vector readings in a magnetic sensor to geomagnetic field models. And so while this is very cost effective compared to the prior method I just mentioned, if there are errors in the model that's being compared to, these errors are going to propagate when measuring the sensor. There's, of course, maneuver techniques where you can have a sensor on your spacecraft and your spacecraft rotates around a known field to understand what the zero level offset and the scale factor errors are in the sensor. And this is also certainly cost effective, but it can disrupt other instruments in the spacecraft. And so each of these calibration techniques have their merit, but they come with their own set of trade-offs. This picture we have below is from the vector and scalar magnetometer method from the CHAMP mission, where you have different flux gate magnetometers, which are vector magnetometers, being compared to this Oberhauser atomic magnetometer. So the solution to some of these problems can be self-calibrating magnetometers, which function as the magnetometer itself correcting for its error, as opposed to relying on different sensors or outside approaches. And so self-calibrating magnetometers already exist, each with their own attempt. There is magnetometers which use microwaves in these atomic energy level transition sensors to create a polarization ellipse where an external magnetic field will affect the ellipse. And how this ellipse is affected can also be calibrated. There are silicon carbide semiconducting magnetometers where the magnetic field affects the atomic state in these semiconductors. And then there's inertial navigation, where you can use chips to detect the gravity, so you know how you're centered in a magnetic field, a known magnetic field being Earth's, and then also using flex gauge magnetometers to compare to this model of where you are relative to Earth's known field. These atomic polarization magnetometers are accurate, but they can become quite costly and complex. The solid state magnetometers are cost effective, they're small, but they can be prone to single event radiation, and there's certainly a lot of room for improving the sensitivity of the instrument. And again, inertial navigation magnetometers are being compared to a model of Earth's known field. And so the errors in Earth's magnetic field and the errors in modeling Earth's magnetic field are going to propagate into calibrating the magnetometer. And so our solution for a self-calibrating magnetometer is to use commercial magnetoinductive sensors and surround them with Helmholtz coils. Now, what is a Helmholtz coil? Well, Helmholtz coils are identical coils that, when put in parallel and driven with current, create a known constant magnetic field between them. And so the difference between this known generated magnetic field versus the magnetic field that, say, a sensor in the middle of them would be measuring is the measurement error. And so these Helmholtz coils are surrounding a sensor called the P&I ARM 3100, which is a magnetoinductive sensor. It's magnetoinductive technology. And so the external magnetic field put on these three sensor axes changes the induction, which can be measured to directly see the external magnetic field that's being put in the sensor. This sensor has been chosen because it's very radiation tolerant, but importantly, it's manufacturable and it's very cost effective. And for this cost, they're very precise and they're small. So it doesn't take up much volume on a spacecraft bus. And it hits a lot of notes where other magnetometers have trade-offs for. And so it's another option for spacecraft that need something that's cost effective while still being precise in high radiation environments. Another benefit is this ARM 3100 is a fully digital magnetometer, which can eliminate error in a hardware sense. So the self-calibration technique is to send a periodic known magnetic pulse onto the ARM 3100. If you send a pulse of current through the Helmholtz coil, it'll create a magnetic pulse of known amplitude onto the RM 3100. And the change from the known peak to peak value of this magnetic pulse we're sending on to the sensor versus what the sensor is reading is the bias of the sensor. And so the calibration consists of a ground calibration where we measure the pre-flight offset and gain bias of the ARM 3100. And then an in-flight calibration where we seek to understand how this ground calibration is changing with time. And so the system, as you can see here, is quite small. It's about a cubic, 7.5 centimeters. So it doesn't take up very much room on a spacecraft bus. And where it's used for is for spacecraft constellations, which are missions that have tens of dozens of sensors. An example of missions would be MagCon or the Magnetosphere Multiscale mission, where they're using numerous spacecraft, where using expensive magnetometers can quickly eat up in an engineering budget. In a perfect world, we would have, unlimited money to be able to use the most expensive, the nicest magnetometers, but when you're sending up numerous spacecraft in orbit, you need something that's manufacturable. You need to be able to create a lot of magnetometers in order to measure magnetic fields and do science in the magnetosphere. And so this is where the Helmholtz RM3100 system comes in, where it's mechanically simple. You have this RM3100 chip and Helmholtz coils, which have been used historically due to their mechanical and mathematical simplicity. It's precise and it's low cost and low power. So how's this ground calibration working? Well, we use this calibration matrix you can see here, where we put our known magnetic field onto it, and then a function of the gain and the orthogonality error in the Helmholtz. What's the manufacturing? How well was this Helmholtz coil made? How are these Helmholtz coils bent? What's the parallel? How parallel is it? How perpendicular are these coils from each other? And so the purpose of this ground calibration is, three large aspects: to determine the functionality of the sensor in order to find these 12 calibration parameters that I was just talking about: the gain, the offset, and the orthogonality, and to find the exact Helmholtz generated field at any given current. The current corresponds to a magnetic field. What current is at what current is the Helmholtz coil creating what field? So what's the ground calibration procedure? So we have a picture of the setup here, where we have the sensor being run with no current through the coils in order to find the zero level off, or just the background field of the sensor, what's going on in the background. And then an alternating current is run through the coils. And so using this oscilloscope, we can find the peak-to-peak voltage across the known resistor. And so the current is a function of voltage and resistance. And so the total magnetic field, the amplitude of this AC magnetic field being generated, is a function of this equation here. And so there's a sine function fit to the data measured from the RM3100, the magnetic field, and the vertical shift of above zero is the offset of the sensor. If there's no magnetic field being put on it, what is it measuring? What's this offset bias in the sensor? And so this is subtracted from the background field in order to find the offset bias of the sensor. And then the amplitude discrepancy from these peak-to-peak values, which we know should be created versus what's being read, is the gain. And so you do this at one magnetic field, and then you can repeat this process across different currents at different magnetic fields in order to find the gain and the linear range of the sensor. So these are very preliminary results, as this is still being prototyped and it's still being worked on. But here's the offset at different observed magnetic fields, where these are different coils in this Helmholtz system. And so we can see the offset observed is generally linear. Granted, this is very preliminary, but it displays some sort of linear behavior of hanging around a certain magnitude of values. And then in the gain, we can see that we also observe a linear gain across around this 100,000 Tesla range. So demonstrating that this ground procedure is trending us towards the right direction of where we are, looking. It's displaying these behaviors. And so the current that was input into it is creating a linear trend of observed versus input magnetic fields. So what's the setup that we've been using for the ground calibration? The initial characterization from those, very preliminary results is coming from a 3D printed prototype coil. And all this is being done inside a 5-layer mu metal shield can. The reason for using the shield can and a smaller shield can is to be able to fit it inside a thermal testing chamber. So not only can we measure what the offset and gain is as a function of input field and current, but also how these offset and gain changes in different thermal temperatures in order to better estimate a space environment. The gain and offset bias is retested inside a large 500 millimeter calibrated Helmholtz coil. And so the discrepancy in the bias calculations between our calibrated Helmholtz coil, which we see a picture of here off to the right, and the 3D printed prototype coil are errors of the Helmholtz coil itself and not necessarily errors of the sensor. And so then the known error of the Helmholtz coil can be subtracted off, and the known error factor from the matrix a few slides ago will not change with different temperatures because of the material used for this 3D printed prototype coil. It has a very small expansion rate with different temperatures, and so we know that the discrepancies from the small Helmholtz coil don't change with temperature when these tests are repeated in a thermal testing chamber. And so using this ground calibration, not only at room temperature, but across different temperature biases in this thermal testing chamber, we can understand offset and gain bias in any spacecraft environment. So the in-calibration, like I said before, wants to understand how this ground calibration is changing with time. And so again, the RM3100 is surrounded by a 3-axis Helmholtz coil, where it's a similar methodology, putting a periodic magnetic pulse calibrates the offset and the gain of the sensor that the Helmholtz coil is surrounding. And so the difference between the positive and negative pulse height is the offset in the sensor, and then the amplitude discrepancy from being measured versus what's being generated is the gain. Now, of course, the RM3100 itself is subject to an internal noise, and so a Savitsky-Golay filter is used to smooth the noise out in order to eliminate that aspect of bias inside the sensor. So electrical power systems already exist on spacecraft missions, but of course the amount of current being put into the Helmholtz coil needs to be regulated to know the pulse height. And so a current regulating system is needed. We chose to use the TI LM317 due to its 0.01 line regulation and its 0.3% load regulation in order to really be able to control the height of the magnetic pulses, so we're confident in the gain and offset in which we're measuring. So What's validation that this can even work in the first place? Well, not just the preliminary results of showing a linear behavior in both the offset and the gain, but we can also do simulation using a small segment from ESA's swarm satellite mission and their 50 hertz data set, which traverses a high latitude in order to showcase the largest effects of gain. What's important too is that this is a magnetically quiet region, so these pulses won't be disturbed by any background effects of either substorms or other spacecraft or space environment happenings. And so to this swarm satellite mission data set, a random gain and a random offset bias, as well as random sensor noise was added. And so using the methodology described from the in-flight calibration procedure, we correct for the data and compare it to the original data. So here's the simulation data, where this is kind of the left picture is all of the axes, kind of shown at once. And then the right is just the BN axis kind of zoomed in, where there's a random offset and gain added to this data snippet here. We can see noise was added as well. And we use the Savitsky-Golay filter, as said before, in order to smooth out the data, looking at the peak-to-peak change to find the gain bias. Then after this gain bias is corrected for, looking at the peak-to-peak vertical shift, I said is gain bias, but is offset bias. That's a typo. And so after doing this, the correction, this here we're looking at is the swarm data calibration detrended. And so we can see how close is our self-calibrated data to the original data. The self-calibrated data being the colored lines and the original data being, this black line. And so as you see, we get a root mean squared error of less than 1 nanotesla, which was our definition of success and accuracy, looking for less than 1 nanotesla root mean squared error between what we are looking to generate, or based on the original data set, which was already calibrated, to then recalibrating. So what's another validation for this experiment? Well, we can recreate the swarm data, the noisy swarm data, using this already calibrated Helmholtz coil, which I was talking about previously. And using the calculated gain and offset bias from ground calibration, correcting for the data set. And so comparing now this corrected data to the original data set before this noisy swarm data was added. So thank you very much for listening. I'll be presenting this information again at AGU and in session SH24B. If you'd like to see a little updates or ask any more questions, and or if you'd just like to meet me. So thank you very much, and I'd like to answer any questions that people have.
Hey, Cole, thanks for a great talk. I have a couple questions, and we'll see if any more come into the chat as I'm asking mine.
Okay.
For something like this, you mentioned low cost, but I'm not sure how much if I missed it. What do you estimate your cost to be for a magnetometer like this?
That's a great question. So you can buy the PNI RM3100 for around like $30 or something on PNI's website. And so Helmholtz coils are also not expensive to make. They're quite cost effective. And so even I think a generous upward estimation would be, materials wise, just $100 at most.
Cool. And so this leads me, does it get more expensive for like a rad hard PMI or is something like that available? Um,
So I don't know what other sensors PNI offers. Big focus has been using this ARM 3100, but a big benefit of the ARM 3100 is how radiation tolerant the sensor itself is. It experiences minimal error up until 150 kilorads.
ah,
Mhm.
cool. So we have another follow-up question by Sergey.
Mhm.
How do you estimate the total mass and power consumption of the instrument?
So the total mass of the instrument, the would hmm, that's a good question. I think the PNI itself is about the size of a US quarter dollar, and it's not very heavy at all. Helmholtz coils themselves don't ever really get that heavy either, don't have much mass to them. So I think while there's no initial estimations of mass, it would, probably be around I don't know. My intuition is really in pounds, so I can't say in grams or anything. But maybe like a tenth of a pound or something.
Okay, so quite light.
Mhm.
Cool. So we have another question from Leonardo.
Mhm.
Looking at your plots, your trends do not necessarily follow the swarm data trend, showing some anti-correlation. Do you have any idea why you have the anti-correlation there?
Yeah, I think it comes from just the fact that the noise added from this, the random artificial noise is going to affect certain peaks randomly as well. And so, because of that, different gains and errors and offset are going to make the trend itself look different. But ultimately, it's a very low error from the original um, data set. I only include the plots of the detrended data instead of just showing the two curves next to each other, because it gets to a certain point where the curves are coming so close that you don't really see anything very noteworthy. But here, the goal is to just demonstrate that while noise can certainly um, affect how this gain and offset is going to create a shift from these trends, they never vary too greatly.
And in a follow-up from Leonardo, do you know what noise you added? Um, I guess what color or what type of spectrum?
I used the SciPy Python library, just random Gaussian.
So I think that's probably white. Um,
Yes.
so one last question from Matthew Finley, who I'm sure you know. Is there an optimal period for the applied pulse to achieve good performance when you're
So
counting?
using the 50 nano or 50 hertz data set, I found that 12 and a half hertz created the most optimal, below 1 nanotesla RMSE.
Okay. And then his second question, is there any reason to do this with the PNI versus something like a traditional spaceflight FGM?
The principle of using Helmholtz coils to calibrate is, very simple and easily understood and can be applied to so many different things. But the benefits of the PNI is its low cost and manufacturability.
Mhm. Excellent. Great. Well, thank you again, Cole. I look forward to seeing your presentation at AGU and hopefully meeting you in person. For everyone else, our next seminar will be next week, and Sam Watson will be discussing characterizing electron fluxes below the inner radiation belt. Um, so I hope to see everyone next week, and thank you again, Cole.